something that is studied at GCSE, but it does go into A-level as well. The sine rule relies upon a triangle being labelled in a standard fashion. The vertex A, capital A, has the side opposite it labelled lowercase a. Likewise for B and C. Make sure that your capital C and your lowercase c are distinguishable. The sine rule says that A over sine A, and again, look at what I'm writing as well as what I'm saying, that ratio, that proportion, is exactly the same as B over sine B, which is the same as C over sine C. Now the nice thing about the cosine rule is that it actually works whichever way up you have the numerators and denominators, as long as you're consistent within the question. Equations that have fractions are always easier to solve if you have the unknown in the numerator, and so that's just a good habit to get into. It saves you a little bit of work. So let's take a look at an actual question. Let us suppose that you had this triangle here. And you knew that this was theta. This was 7, perhaps 7 centimetres, but I'm not going to worry about units in this question. 10 there, and 20 degrees there. And you're supposed to work out the value of theta. Just tidy that up. Okay, now it's all about angles and their opposite sides. So I'm going to write down that sine of theta over 10 equals sine of 20 over 7. I'm going to multiply through by 10, so that sine of theta equals 10 sine 20 over 7. Sine of theta therefore works out at, let's see, 10 sine 20 all over 7, 0.489. And at GCSE, you would typically just inverse sine of both sides and discover that theta is 29.2 degrees to one decimal place. However, we have a bit of an issue, because you should know by now that the sine curve can produce more than one solution. And so we actually need to just make sure that this is the only solution. There's your sine curve between 0 and 360. Sine of theta equals 0.489. 0.489 is about there. And so there's a solution there, and there's also a solution there, as well as numerous other solutions if we were to move backwards and forwards along the sine curve. So there's the 29.2 degrees that we got. What about this angle here? Well, this is 180 degrees. There's a line of symmetry through 90 degrees. And so we can judge that this other angle must be 150.8 degrees. Question is, can that exist inside a triangle? Well, of course it can, because triangles can have obtuse angles in them. I know that I drew the original triangle in such a way that theta looked as if it was acute, but the question didn't say that it was acute. So we've actually got an interesting situation going on here. The angle can also be 150.8 degrees. And what's happening if we just try and sketch these two triangles that we've discovered? The first one, let's try and make it reasonably realistic. 29.2 degrees is a small angle. 20 degrees is also a small angle. So in the first, more understandable situation, 29.2 degrees, 20 degrees, 10 and 7. That's believable. But we've also discovered that there's another situation where you still have your 20-degree angle, but this triangle can exist as well. So this now has 150.8 degrees here, 20 degrees here, 10 there, and 7 there. There are two triangles that fulfill the original conditions, and you have to be quite careful using the sine rule to make sure that if there's a second angle, that you do actually find it.